So as I said, today is drilling into some more of the kind of technical aspects of AI and machine learning and some of the things that you'll need to put in place if you start leveraging artificial intelligence, machine learning, and primarily in the space of building your own bespoke solutions. So instead of using off-the-shelf kind of plug and play style solutions, building up your own intellectual property, customizing and products, doing research and development in improving processes and the way things work specific to your organization. First of all, a recap on what AI is. So AI performs cognitive tasks. So that's reasoning, understanding, and listening, and interacting. Sorry. We should also listen as well as part of our interacting. So reasoning is, how do we go from the things we see, the data that comes at us in the world, and turn that into rules and ways of operating. Understanding is how do we interpret the sensory inputs we get from sight, text, voice, and so on. And then taking the reasoning and understanding capabilities and actually providing a more natural interface between humans and computers so that people don't have to code. They don't have to necessarily be particularly specific, but the computer understands enough to be able to perform the correct task. It's kind of the holy grail, really, where instead of computer doing exactly what you what you tell it to, it does what you wanted it to. Those three tasks split up into kind of certain specialisms. So computer vision is working with images and video. So with computer vision, we can do things like detecting health and safety risks on the shop floor. We can use natural language processing to process the text from field reports and news and academic papers to be able to extract insights about what's happening. Conversational interactions allow us to add chatbot type of interfaces to our processes so that people can have a more intuitive way of interacting. Speech processing allows us to communicate across multiple languages and be able to do things like real-time translation of what we're saying in real time. Knowledge mining helps us put together a map of how things work and extract facts from text. And then induction is the area of taking a lot of data and trying to condense that down into rules. Humans are fantastic induction machines. We, very early on, we start hearing words and we start putting meaning to them, and we're very good at it. And this ability to go from specifics to general underpins a significant amount of the other areas of AI. So we're going to be looking at kind of the deeper level than the AI use cases today. If you need to take that kind of high level step back to what can AI do for you, we have that in a prior video. I will reference some of these use cases as we go along, but today we're focusing more on the machine learning side of things and data science, and how these kind of actually work in terms of methods, so that you understand how, when you have a business challenge, you can say, that is this sort of machine learning or data science challenge, to be able to go and effectively source the right solution. So to recap on the use cases, AI and machine learning can be used to help with quality control, generative design, help you understand when there might be problems with your system so that you can get repair people out sooner before a significant failure happens, but also be able to streamline your processes so that you have to do less overall maintenance and be able to do maintenance at the right time so that your costs come down. And it can be used behind the scenes inside your headquarters and with your staff to automate grunt work and repetitive processes that are kind of in the knowledge worker sphere. So getting down to the brass tacks, what is AI and machine learning in terms of techniques that underpin lots of the different kind of solutions and use cases that we could be doing? So first of all, the core AI tasks that we were discussing earlier include computer vision, speech, and language. And almost all of these use machine learning behind the scenes. So somebody will have built a machine learning model to identify stock and brands and defects and other things in a vision setting. Or they might have learned how to translate sounds into text by taking the sound waves from a recording and comparing that to the text words, and ending up with a complicated rule set that goes from this sound to this word. So AI, these kind of cognitive tasks that we're doing, typically have a machine learning underpinning. If you're using AI without trying to kind of do your own R&D associated with it, you are usually relying on other people's models. That has some advantages. So somebody like Microsoft or the OpenAI project and things like that, they will have access to a huge amount of data that can be used for training purposes. They might have invested very heavily in acquiring that data. The great thing is that whether you use the straight off-the-shelf solution or some of their customizable ones, you can leverage their intellectual property, their research, their data to be able to get your own job done. And the customizable ones will usually have you putting in your specialist images or jargon or whatever, and the off-the-shelf solution will kind of tweak itself to be more specific in your situation. All of it happens through techniques like transfer learning, and that is kind of where a lot of the technical bits and where you might end up with your own technical staff doing these kind of research and development tasks. So we're going to look at the core kinds of machine learning that underpin these AI types. So there's 4 key things that we do with machine learning and induction. One is we try and predict values. So that could be trying to predict how much a unit will sell for, how much defects we might expect, what our cash flow is going to look like today, tomorrow, and the next day. There's a wide variety of things that we would usually try and predict value-wise. Then we often want to predict labels. So predicting labels is things like predicting outcomes. Will this machine break down or not? In this image, is there a product or is a product missing? That kind of label is something that has a probability of showing up, and that's what we end up trying to predict. We can use machine learning to discover patterns in our data. So the classic example of this was Walmart. Walmart have been one of the pioneers of kind of data science in business for decades now. They discovered that beer and diapers often sold together. It's a bit counterintuitive, but it turned out because they found from user research that it was basically dads on the way home from work would be told that they had to pick up diapers, and since they were in the shop anyway, they'd pick up the nappies and they'd pick up a crate of beer. So Walmart put those two together to be able to increase the amount of cash that they earned in a quicker space of time. The other key area, which is particularly useful in a manufacturing setting, is the ability to discover anomalies, to find out when processes are deviating from normal in possibly a very sophisticated and distributed way, and be able to intervene before something goes wrong. So we're going to look at labels, patterns, and anomalies, and some of the key methods that we use as data scientists and machine learning engineers to solve these types of challenges. As a business person, when you're thinking about the thing that you're trying to solve, if you can work out whether you're trying to predict a value, a label, identify patterns, or identify anomalies, that helps greatly speed up the process of going from business challenge to real value. So keeping just those 4 high-level things in mind helps you greatly. So the first area that we're going to be going into more detail is classification. So this is where you try and predict a label. Basically, do you classify this thing as something or another? So here is a classic example for things like predictive maintenance. You need to understand the drivers of whether something is going to break down or not. So what you do is you get lots of data about the machinery, some external factors, things like last maintenance date, repair record, if it's something that's out in, if it's outside, what has been the temperatures recently, and you get all of this information together and you use it to try and identify, based on those pieces of information, was there a breakdown or not? So you usually know that answer, and then the algorithm behind the scenes tries to generalize from that noisy data to the sets of rules that govern whether there's going to be a breakdown based on the data. So we can say that as the RPM increases, the chance of breakdown increases, that there is an interaction between temperature and RPM. So if you find that the machine's moving faster than it should, and it's a hotter day, then you're more likely to get a breakdown. So you can use it for insight. So creating an understanding of how the system works so that you can put in manual interventions, Or ultimately, you can put these sorts of solutions in an automated fashion so that they generate work orders for approval to before something breaks down, so that you can get a person out without needing a long decision time about there being a possible breakdown. 3 key ways of performing classification are decision trees, regression, and neural networks. So a decision tree is basically a set of if this, then that types of rules. They can get very complicated. You can end up with, if you had 200 sensors on your machinery, and you were trying to predict whether there was going to be a breakdown, a decision tree would sift through all 200 sensors worth of data and try and work out the right if this, then that boundaries, possibly to kind of 200 levels of complexity. There's lots of different variations. So once you start getting fancy with it, you end up not just with a single tree, but you end up with jungles and forests. So you might hear somebody talk about random forests. It's not it's not like a computer game or something. It's basically just a lot of decision trees that have been combined together to get a more sophisticated result. Then there's regression. So regression is our classic making a line of best fit. It works across multiple columns and parts of our data, but the idea is it's just trying to effectively build a straight line by default. So whether something happened or not, you can't say something half happened. So it ends up predicting the probability or the odds that something happened. So you end up with a really fine-grained control to say, not just will it happen or won't it happen, but we're going to set the threshold to 70% probability of a breakdown so that we don't use our scarce engineers' resources on too many false alarms. Neural networks, this is the area, this is the most common type of algorithm in deep learning. This self-optimizes. So with a regression, it will go through and try and find one line of best fit and say, here you go, here's the rules. A neural network takes all of the possible columns and sensors and things that you plug into it and tries to build a regression, and then goes through and optimizes itself a number of times with the aim of producing a more accurate solution. Neural networks tend to have more accuracy as a result, but they usually need far more data, and they aren't as explainable as decision tree or regression-based methods. So in a situation like autonomous vehicles, you probably want it to be as accurate as possible so that it doesn't crash as often. The problem with that, as we try and get that more accuracy, is we have the challenge of explainable AI. How do we know that when the car turned, it turned for the right reason? So that's an area of complexity and ongoing research, lots and billions being chucked at it to try and make these more sophisticated classification capabilities more explainable, more auditable, so that longer term we can have more trust in them and put them into more autonomous scenarios. decision trees and regression models are usually there for insight and can be used in autonomous situations, but they usually end up with effectively a human supervisor. Instead of them always acting independently, sending control messages to machinery, they're usually used to inform before, and then a human assesses whether to do. I said earlier that anomaly detection is particularly important for manufacturing. So we have thousands and thousands of sensors generating real-time data about how the machinery is working. And everything is getting more and more sophisticated and more data. Trying to correlate problems and when sensor values start deviating from the expected range, and knowing when that deviation is going to cause quality issues or cause production issues or potentially indicate a breakdown or a significant risk to operators, that's really vital. So anomaly detection is the part of discovering unusual values. And there's 3 types of unusual values. The easiest one to monitor for is a point anomaly. So this is just, this value is outside the expected range. Classic monitoring has been doing this for years and years because it can be quite easy. You can set something as simple as if a value is outside the 95th percentile or 6 sigmas out, you can fire an alert and give somebody a heads up. But that tends to generate a lot of, that can generate false positives in a situation where values might be cyclical or might have a wide range. The next level is contextual anomalies. This is usually based on a few values that have happened before it. Is this value unusual? So in a situation where RPMs are increasing throughout the day, if you get a sudden drop in the value to maybe like 50% of what it was a minute ago, that would be an anomaly that's worth pointing out then, but not at the beginning of the day. So contextual anomalies start building up from what's happened recently to be able to say this was an unusual activity. So that gives you far fewer false positives. And then typically a somewhat retrospective view is collective anomalies. So this is where where over time values were unusual, where they didn't fit the expected pattern. This becomes, this one is a lot harder to detect in real time, but is useful for things like detecting quality defect patterns, or can be fraudulent transactions and tampering with systems. So there's 3 different levels of anomaly detection, from point to collective. Point being the easiest and least sophisticated set of algorithms or rules to implement, and collective being the most sophisticated, least likely to generate false positives. For detecting patterns, we can use the detection of patterns for identifying groups inside stuff that doesn't currently have labels, or we can use it to find associations or correlations between different things. So the most common clustering method, and one of the easiest to do, is called k-means clustering. K is basically the name for the number of clusters that you have, and it tries to create new points inside your data and say how close are different records to this data. And then it ends up being able to say these records are all close to each other, they belong in cluster 1, these values are all close to each other and aren't close to cluster 1, so those will be cluster 2. The value of this type of activity is you can find groups that you didn't know existed. So more in kind of the retail, financial sectors and things, people use this to discover customer groups. And you can do that if you have a lot of downstream customers. But you can use this, people have been doing, there's different studies that use clustering to try and detect correlated factors that relate to rework, saturation of kind of and bottleneck inside the shop floor. We can use hierarchical clustering to basically build almost like a decision tree that, instead of trying to optimize for an outcome, for a label, for trying to build a decision tree that groups, that the end values, end groups are as dissimilar as possible from each other. One of the great things about a hierarchical clustering model is you can take groups at any level. So you could have the first split having only 3 groups, but then like all the way down at the bottom, there could be 300 groups. So this was the type of technique used by Tesco's when they made their club card customer segmentation model. This can be useful for things like categorizing SKUs. So I've worked with logistics companies who have ended up with kind of 1.5 million line items, and they have some free text and they have some properties about all these different things, and trying to maintain a taxonomy, a way of grouping all of these products, is really difficult. So what we usually do in that sort of circumstance is we put things like lead times, transaction volumes, profitability. We turn the free text into little tokens and words, and we use all of that data to try and say, these are all nails, these are all widgets, and able to have that at different levels so that they can start optimizing inventory and ordering processes and things for that at different levels of detail. And then the other area is associations. So this is the beer and diapers Walmart type of situation, or the recommendation engine that tells you what to watch on Netflix. This kind of situation or association method is great when you're trying to find patterns in why things go wrong, or try and get a view as to what's normal, or how you might optimize your stock or inventory or optimize prices based on what you have in stock. So it can be really useful for upsells, stock management, and things like that. Okay, So that was hopefully not something that made your brain bleed, but a high-level introduction to some of the techniques that data scientists and machine learning specialists will use to solve specific business problems for you. For them to be able to do that, or for you to even have a go yourself, because there's a number of graphical data science tools that you can use, some things are really key to be able to ensure that you can do it. So this is kind of what is the critical infrastructure that you need to be investing in. So the first thing is you need to be investing in your data. Like any asset in your organization, if it is not maintained, if there are not quality processes and documentation and considerations around compliance and all of these things, this data can kind of become toxic. It can become untrusted. It can rack up costs unnecessarily. So you should be treating data like any other company assets. Company assets to be valuable and are maintained. So you can be collecting data from the different sensors in your operating environment. We did a session last week called The Historian and AI, where we look at the historian appliances and how you can get data from sensors in an aggregated, in a consolidated way. Your ERP and logistics systems are a wealth of data, whether it's metadata that tells you about the product you're building or the fleet that you're using to ship things in, or who your staff are. The ERP data is usually really vital for being able to make sense of all the other stuff that's happening in the right context. So getting data from your ERP is making sure it's good quality doesn't just help the business perform better day to day, but will also help build these bespoke machine learning tools to solve business problems. Then there's events. So an event might be a breakdown or a repair or an alert, a stop sign or an accident, but the kind of things that happen and aren't a continuous thing. Some of these things like breakdowns and stuff might come through your Internet of Things or a sensor network. Others might get logged even in spreadsheets. So you need to be thinking about these events, because usually one of the things that you're going to want to do is try and predict whether an event is going to happen and do classification. If you're not collecting rich data about those events, you might struggle to be able to connect the dots between stuff that happened and whether an event was caused. And then there's also third-party data. You don't just have to rely on the things that you build or get data on internally. Again, coming back to Walmart would have a just-in-time logistics process for delivering goods to their stores that included the weather. So that would enable them to know when to ship ice cream and barbecue coals and all of these other things, because they could say in the next 5 days we're going to have a heat wave, so go put a load of crates of beer in the trucks and get them to the stores. This helped them optimize their inventory and increase sales. So integrating weather data, you might get your suppliers and your customers to give you data feeds, returns, stuff like that. all of that can be used to integrate in and give a richer perspective on your business. And this is just kind of the 4 key areas. There is tons and tons of data being generated in your business every day that ultimately you will want to catalog and explore the value of. These days, because we're getting data from lots of disparate sources, lots of different systems, it comes in at different speeds. Like you might get a weather forecast once a day, but your sensors on all your machinery's generating data continuously. Trying to join this up in the classic database has been very difficult. So relational databases say these pieces of information about suppliers and these pieces about our inventory often match up when we make an order. And that's great for a system where you know what's happening and you know the full scope of the things that you're going to ask. But it isn't necessarily very good when you're rapidly getting lots of changing data with potentially changing attributes. So pre-COVID-19, we were not going to, we didn't need anything about metadata around social distancing and the staff practices around masks and all sorts of things like that. But now we're going to have to ask all of that kind of thing, and at least consider how we store and log it for compliance and health and safety. And adding those extra fields or doing that domain modeling exercise could be kind of costly and slow the company down from being able to gather that data in the first place. The idea of the data lake is that you just almost like dump all the data in as it's coming in into effectively a big file system. It's usually a bit more complicated, definitely should be better structured, but the idea is instead of trying to do the this is how our business works and this is what I expect to see at the point of bringing in the data from the different places, you say, I'm going to take the data as is, and then when I need to know something, I'm going to say, this is what I want to know, and operate on the files to extract that piece of information. So there will usually be multiple data pipelines that kind of siphon specific filtered views of the data that has come in and being consolidated in the data lake. And then those standardized views that we know the business wants to see, those can go into databases or be used to produce real-time alerts or be used by data scientists to train a new model. And we can have lots of different pipelines working on different views of the data. You do have to be careful, very, very careful with a data lake, because your data is an asset, and if you treat it carelessly, it becomes a mess to handle. So there's usually recommended structures for kind of how you store it. There's data catalogs, so you add metadata about what you have, where it's from, who should be allowed to access it, and things like that. So there's a lot of longer term practices that you should be kind of exploring, but the data lake is a low cost way to be consolidating data from lots of sources without substantial setup time. You tend to pay a little bit more time on the utilization side for creating the definitions as to what you want to be extracted, but you start capturing the data and storing it sooner, and you can always take a new view of that data, but you can't get back the data you never captured in the first place. How things like the data lake and critical infrastructure fits into your organization is usually dependent on how sophisticated you are with data right now. So if you only have like some spreadsheets and they're crashing all the time and people are hollering to say, I need to go into the spreadsheets, it's probably not a good idea to try and run with machine learning whilst you're at this stage. So at that kind of early stage, we recommend getting software that has AI built into it and that leverages other people's data. So this starts you on your journey of becoming a more data savvy company, because you'll start seeing in that software where data quality problems are causing the solutions that work well for others to not work quite so well in your situation. You also probably need some external help to start you on that journey. If you have some data and it's kind of going in to maybe a database, and you've got some developers or some people who can write some code, and you're relatively comfortable with the data, you can be adding some off-the-shelf APIs to do some things like add captions to all the images that field engineers have taken. And you can do that without needing to have a lot of integrated data from different sources. You can use other people's models to be starting to enrich your own data and be able to improve processes. As you're combining, if you're at the point where you have data coming in from IoT, you've got your ERP data accessible, and you want to start working on trying to do things like predictive maintenance and stuff, you can use tools like Power BI, Azure Machine Learning Designer, Data Robot, and a few other kind of tools to start trying out different models, to take people who are not necessarily specialists, but can start using guided workflows to start understanding the key drivers behind things like breakdown of machinery. Next step is building your own bespoke models, and you usually have people who understand the mathematical principles behind the different types of models and can help guide you to the right solution, and build on your data lake or your relational data and your IoT data to come up with custom models that are well tuned to your situation. And then the next level up from that is, once you're comfortable with models being generated and kind of AI and machine learning solutions being used to drive insight and decisions inside the business, is you can start training these models and then actually deploying them on the device. So you can have the real-time monitoring of your machinery, not needing to go all the way through into a historian and then into the cloud and having a latency of maybe like 5 minutes, but actually having it go there and then. I see a problem, I'm going to start fixing it or sending up an alert. So that edge AI requires good quality data, grown trust, about the quality and the impact that it can have. So yeah, you can go from spreadsheets to Edge AI, which sounds really fancy, over a few years. Okay. So next steps, now that you've kind of seen a bit more of the technical detail about the types of machine learning solutions that can be built and some of the different subsets, and how you go from how you start working with your data to be able to capture it and support machine learning processes. You can be thinking about these in terms of the key areas of AI. The core techniques underpin almost all of these solutions. So knowing how a decision tree works helps you understand how these processes can work. There are tons and tons of use cases inside manufacturing, and it can be used to improve safety, increase productivity, lower costs, and improve profits. The process that you'll go through is starting out with your business problem, or where there is a challenge or a room for improvement. You identify the goal. You can't do anything without a number against it. So what are you trying to optimize for? Are you trying to optimize profits, reduce overheads, increase safety? Have a critical measure that gets used. Look at whether you have the right staff for it. Build a prototype. If you're happy with a prototype, start looking at how you can put that into production, how you can scale it. Does the lessons that you've learned in getting to that prototype help you apply the same concept across the organization? Fundamentally, building models is like any R&D effort. You go from a business need to requirements to design, initial implementation, and iteration. To help you learn more, obviously we've hopefully you know now that there are there's two preceding webinars on the high level, and historians and kind of the anomaly detection side in particular. We've got our 7 quick win AI projects. We do have some exciting news coming out for part of that, which I look forward to being able to tell you all in the next few days. And we've included some case studies for some of the different ways people are using AI and machine learning in manufacturing. As an organization, we love helping businesses adopt artificial intelligence and other emerging technologies. We think most of this isn't a technical problem. We think it's a people and process problem to make sure that everybody understands what to do, who's going to do it, and making sure people are equipped to do it. So our 3 products, AI Direct, AI Learn, and AI Connect, help resolve the people and process challenges for businesses to successfully adopt AI.